A team of engineers were trying to measure the height of a flagpole. And they were using a measuring tape, but they kept having trouble because they'd put the tape up and the tape would fall down. Finally, a mathematician walks by and sees their dilemma. So he takes the pole out of the ground, lays it down, and measures it quite easily. As he walks off, one of the engineers says, "Just like a mathematician, we ask for the height, and he gives us the length." And today we will be talking about special segments of triangles, including the height or altitude, mid-segment, well, we already did mid-segments, angle bisectors, medians, and perpendicular bisectors. Now, one of the words we will be using today is equidistance. It means equal distances to two or more points. So when I drew this circle here, so you can see the center of the circle, and both of these segments, AC and CB, are equal lengths. The distance from A to C and B to C is the same. So all the points on this circle are equidistant to point C. Now, how does that come into play? Well, right now I'm just going to look at a perpendicular bisector of a segment. I'm not worried about triangles yet. So if a point is on the perpendicular bisector, that means, first of all, the bisector divides the original segment into two congruent segments. So you know that M is an equal distance to A as it is to B. If I move up the line, E is also equidistant to A and B, and D is equidistant to A and B. It kind of creates an isosceles triangle. If I were to pick any point on this green line and connect it to the two yellow points, A and B, I would have an isosceles triangle. Now, perpendicular bisectors of triangles, while all the points here on this dotted line are equidistant to B and C, then you have all the points on here on this dotted line are equidistant to A and C, and all the points here on this bisector, not an altitude, are equidistant to A and B. For my pre-AP kids, this point where they meet is equidistant. It's an equal distance to all three vertices of the triangle. And you could actually make a circle that runs through all three vertices of this triangle with the center here. So this is one of the special words. It's either an orthocenter, centroid, or, and the other one's escaping my mind for the moment. Orthocenter, centroid. Okay, now let's go ahead and take a look at example 1. Find X and EC in the triangle at right. So this is a perpendicular bisector of the segment AC. What that means is that the two segments are congruent. This segment AE and this segment EC are the same length. So I'm going to set both those values to equal to each other. Then I can solve for X by subtracting 3X from both sides, then add 7 to both sides, and I get 8 equals 2X, or X is 4. So I found X, that's part of my answer. Now I want to find out how long is EC. I will go ahead and substitute this value of 4 into X up here. So that means that EC equals 5X minus 7. Substituting in the 4, 5 times 4 minus 7, 20 minus 7 is 13. Now, we're still using the same problem, so I'll put some of the values we already know. This was 13 from the previous problem. Since this is a perpendicular bisector and these segments are congruent, then I know that this is also 13 on the left. And they want me to find length AD. Well, one of the things that's important to know is that it's perpendicular, so that means this is a 90-degree angle. So I have a right triangle. If I know this length, then I can use the Pythagorean theorem to find AD. So I go ahead and substitute in the X equals 4 in there, 2 times 4 plus 1, which is 9. Now I use the Pythagorean theorem. 13 squared plus 9 squared equals AD squared. So I have 169 plus 81. Then I get 250. So AD is the square root of 250. Now for my pre-AP kiddos, you can actually simplify this radical so that you can rewrite it Let me go ahead and do that for you. So you can rewrite it by doing some factoring. Now you could, ideally you would do a prime factorization. Right now I'm just going to go ahead and notice that there's a perfect square in there already. So you pull out the perfect squares, factor them out, and then you take square roots of each of the factors. So square root of 25 is 5, and we get 5 square root of 10. So that is called simplifying the radical. Now, an altitude, you learned about altitudes in 6th grade because you were actually finding areas of triangles back then, and the altitude was a major part of finding the area. So it provides the height of the triangle from the topmost part, which would be the vertex, down to the base. So it is always perpendicular to the base of the triangle, and it has the endpoint at the opposite vertex. So CD here in this triangle is the altitude, or the height, and it's inside. And you're used to dealing with triangles where the altitude's inside. But if it's actually an obtuse triangle, like this one right here, the height actually lies outside of the triangle. So you can extend the base here, and you can see when you drop straight down, then that altitude is outside of the triangle. For right triangles, oftentimes, not always, but oftentimes, the height will be one of the legs of the triangle because you already have a 90-degree angle there. Each triangle can have 3 altitudes. So I have an altitude here. I could have an altitude if I rotated the triangle, and then I could have an altitude rotating it again, kind of like when we had the 3 perpendicular bisectors. All right, now let's go ahead and take a look at this example. Right now, I have a height right here. I could have had a height Q coming on down, but for right now, this is all I have. And they tell me that angle STR is 3x plus 6. Well, since this is an altitude, then I know that this angle is 90 degrees. So I can go ahead and set up an equation, 90 equals 3x plus 6. Solve for x by subtracting 6 from both sides using the subtraction property of equality. Divide both sides by 3 using the division property of equality. And I get x is 28. So that tells me that angle Q, which is just x, is 28. I can also substitute back in and find what angle S is. It's 63. Now they want to know angle QRS. Well, what is angle QRS? It's this angle right here. If you get stuck on your angles, always start from your the first letter to the middle to the third, and you can see that that whole angle right there is what they're looking for. So I'm going to use the sum theorem for triangles that all angles add up to 180. And I have the measure of angle QRS plus 63 plus 28 equals 180. As combine 63 and 28. And subtract 91 from both sides, and I get angle QRS, the measure of it, is 89 degrees. Now, angle bisectors is our next to last segment. It bisects an angle of a triangle and has one endpoint on the vertex of the angle and the other endpoint on the opposite side of the triangle, and it creates 2 congruent angles. So basically, an interesting thing for my pre-AP kids when you come to this question is that every point on here is equidistant to this side and that side. So you can actually draw a little vertical. So it comes into play when you have 3 of these, that the place where they meet, which will always be inside the circle, inside the triangle, will be a special point. And so that's another special center for you. And what you can do is you can actually, where the 3 meet, that's the center of a circle that lies exactly inside of the triangle. Now, the important thing for most of your problems, for everyone, not just pre-AP, is that it creates 2 congruent angles. All right? So this angle will be congruent with this angle, every angle bisector. And let's see, you have your vertex, one endpoint's a vertex, and one endpoint's the point on the other side. There is no guarantee that AD will be congruent with DB. So in example 4, I know that CD is the angle bisector of ADB, and I also mixed it up a little bit and said it's also the altitude of ADB. Well, the altitude, and then they tell me measure of angle A is 43. Altitude means that this is a 90-degree angle. So I have 43 degrees and a 90-degree angle. I could find this angle. What I'm trying to do is find all of the angles. So let's start with this one. And I know I have a triangle right here. And you remember the corollary, the complementary angles in a right triangle also have to add up to 90. So that kind of shortens my work just a little bit. 43 plus this angle here must be 90 degrees. I could have done 43 plus this angle plus the 90 equals 180, but it's actually going to simplify out and give you the same answer. Subtract 43 from both sides, and I find out that angle is 47. Now, since it's an angle bisector, that means these two angles are congruent. So I have 47 here and 47 there. I can equally find the measure of angle B. You see, I have, this is actually a right angle here as well. So these are like two twin triangles. So I have a 47 there. That means this has to be a 43. And this is 90 degrees. The median is basically has one endpoint on the vertex and the other endpoint on the midpoint. It is not necessarily perpendicular, but it does create two congruent segments. So when you have the medians meet, that should give you a different center, and that's probably their centroid, orthocenter. Oh, circumcenter. That was the third one. Centroid, orthocenter, and circumcenter. So we're going to use the median, the fact that it cuts something into two congruent angles, and what will that be? So first of all, let's go ahead. We know that this segment has to be the same size as that segment. So I know they're congruent. Why? Because the median hits the midpoint. So I set those two values equal to each other. 4 equals 5a minus 6. Add 6 to both sides, and I get 10 equals 5a. Divide both by 5, and 2 is a. So now that I know 2 is a, I can actually find out this length over here, which is 2 times 2 minus 1. 4 minus 1 is 3. Now we want the perimeter of this triangle, which means I have a 3 and a 4. So I still need to find this edge right here. So this is 3, that's 4. If you know your Pythagorean triples, since this is an altitude, that means that's a 90-degree angle. And I can use Pythagorean theorem. So using that, you get 3 squared plus 4 squared. But I recognize this as a triple, so I know it's 5. It's the 3, 4, 5 right triangle. To get the perimeter, we add all three sides. I add the 3, the 4, and the 5. And I get 12. Now we're going to go ahead and find the perimeter of the larger triangle. Well, now I know that this is 3 and this whole length is 8. This is still a right triangle here. So I'm going to use the Pythagorean theorem. 3 squared plus 8 squared is this squared. So I have 9 plus 64, 73. Take the square root of both sides, and this length right here is square root of 73. Now, to find the perimeter, I'm going to add all three sides together. So perimeter equals 3 plus 8 plus 73. As a radical, you cannot really add to the numbers, the other numbers in the equation, unless you change it to a decimal or something. But I prefer you give me more exact answers without decimals. So this is a fine answer for me. Just combine the 3 and the 8, add them together, and the perimeter is 11 plus the square root of 73. So for reflection, I want you to think about a segment that is an angle bisector and a median at the same time, and it would also be another special segment. You might want to draw a picture. I've already shown you one where it was a median and an altitude at the same time. That picture could be helpful. And for my pre-AP, you have also an extra assignment. I want you to define the orthocenter, the circumcenter, and the centroid of a triangle. And how are they related to the special segments in this lesson? It's also important to know what are they equidistant from.